Welcome to Brain Vision.
In this problem, we're told that we have what they call a strong back here, which is the beam that has some attachments here and some cables running up, and then would be attached to a crane or something. And this is basically used to pick up loads and essentially take the stresses off the loads as much as possible. So what we have to do is we're asked to find the placement of these hooks here, the distance from the end, so that the moment in this region of the beam here is 0. And the only reason we can do that is because we have these things are offset from the beam. And so if we look from the center of the beam to the point where these act, that is 0.2 meters. It's also, these are offset too by little flanges that are attached, but it doesn't, that distance actually doesn't come into the analysis because these forces are vertical. So we have symmetry here because we're lifting a uniform log or bundle of wood or something. And so these two forces are going to be the same, and they're going to be half of the load, which is half of the load is 1 kilonewton. And then this angle here, I should write this in, this angle is theta, this angle is also theta, and that's 45 degrees. So what we find, this is F2, this is F2, and this is also F2 because of symmetry. So we find that F2 equals F1 times the cosecant of theta, or F1 over sine of theta. So that's the magnitude of these forces here. Now the moments, we can take moments, if we look at we take a cut. So I took a cut at an arbitrary distance x in from here. And we take this cut, and now we can look at this free body diagram. And in moments, we have this distance times the vertical component of F2, and then this distance, which I call W, from the center of the beam to where this cable is attached. The vertical distance is W, so we have minus WF2 cosine of theta. And then here we have x, whatever this arbitrary distance is, times v1, and then plus m1. We can then solve these two equations for v1 and m1. And interestingly, and kind of surprisingly I suppose, is m1 does not depend on x. So in fact, anywhere in this region we are going to have the same bending moment. And we want that to be 0. So we can find m1 is f1 times w cotangent of theta minus d. And we set that to 0, and we find that, and that tells us that d should be w times cotangent of theta. Cotangent of theta is actually 1, because theta is 45 degrees. And that tells us that d has to be 0.2 meters, which is the same as the height above, here. So these things need to be way out here towards the very end. Since this whole thing was 6 meters, we need this to be needs to be very close to the ends here, which would mean that this beam here would have would have 0 bending moment in the vast majority of the length.